Bismillahirrahmanirrahim. After studying conformation isomerism in acyclic systems, today we are going to study how the conformation is in cyclic systems. Remember, rotation is not possible in cycloalkanes like acyclic system because here the ring concentrates the movements around the carbon-carbon single bond. In the cyclic system, the angle of 109 degree cannot be attained, and this causes the angle strain. And in planar rings, there are many eclipsed hydrogen atoms too, which creates torsional strain. Both these factors increases the energy of the system, and the order of increase in the ring strain is cyclopropane is greater than cyclobutane, which is greater than cyclopentane, and which is greater than cyclohexane. So as the number of ring forming atoms increases, the ring strain decreases, and number of possible isomers also increases. In the small rings like cyclopropane, the conformational flexibility is very low as its formation is also very low. The flexibility of 4 and 5 membered rings is significantly greater, and these molecules exist as a dynamic equilibrium among various occurred conformations. Let's see how the rotation of sigma bonds in cyclic compounds may occur. For example, you can see that in this case, the sigma bond in this cyclic system are in rotation, and rotation is very limited as compared to acyclic systems, which we studied earlier. You see that there is very limited rotation of this sigma bond, which is giving and resulting in the formation of different conformers of the compound. Although there is conformation, but to very limited extent as compared to acyclic systems. Now we will discuss conformation in each of the cyclic compound members individually. First of all, let's discuss conformation in cyclopropane. The cyclopropane is a planar and flat. It means that the molecule of the cyclopropane is planar. You move it in any direction, you see that the number of all the atoms are aligned in a single plane. So such systems are called planar systems, and the molecule is a planar molecule or a flat molecule. The carbon atoms at the corners of equilateral triangle, the bond angles which are almost 60 degree. You see that the bond angles, all the bond angles are of almost 60 degree. You rotate in any direction, you will get the same result. The angles are of 60 degree approximately, and they are much smaller than the 109.5 degree angles in the tetrahedral carbon atom present in the straight chain compounds. And the resulting angle strain, which is obtained by subtracting the present angle from the standard angle, is 49.5 degree, and is very dramatically influences the structural and chemical behavior of this cyclopropane. Cyclopropane also suffers substantial eclipsing strain since all the carbon-carbon bonds are fully eclipsed. You see that in this compound all of the carbon to carbon and hydrogen to hydrogen atom are fully eclipsed as the molecule is planar. So there is substantial eclipsing effect. As a result of this, cyclopropane ring have little conformational flexibility. So formation of conformational isomers in cyclopropane is low, and there is only one conformer possibility in the cyclopropane, which is shown here. Only this structure is possible due to low conformer formation possibility. Only this form can exist. And we also saw in above charts that order of increase in ring strain is cyclopropane is in highest order, which means number of possible isomers in cyclopropane is lowest, and as the number of ring members increases, possible formation of conformers also increases. Now come to the second example, which is the cyclobutane. In the cyclobutane, some bond eclipsing strain is reduced by folding and the total eclipsing and angle strain remains high in this case. Due to angle strain in all internal angles are of 90 degree and the hydrogen are eclipsed due to torsional strain. The angles are of 90 degree between different carbon to carbon atoms. We see it here in three-dimensional molecule. You can see that different angles, all of the angles in this case are of 90 degree. Even in the puckered form, the angles are of 90 degree. As compared to the 60 degree angle in cyclic propane. The molecule is puckered as shown. You see that in this diagram, this molecule and the second form, here a little puckered form can be seen due to the movement of these sigma bonds. There is a slight rotation in these bonds as a result of a puckered form is uh, formed. This puckering also relieves eclipsing, which relieves the torsional strain, and hence this puckered form is more stable than this planar form. The cyclobutane molecule exists as a dynamic equilibrium in between these two structures. So the actual structure of the molecule lies in between these two molecules. These forms are more clearly shown in these diagrams. You see that here is the planar form and it is the puckered form of cyclobutane. This is the planar form where the atoms eclipse each other, while this is the puckered form where the eclipsing is a little bit diminished. Moreover, the molecule is not planar as compared to this form. You see that a puckered and bending in molecule is seen in this character. As a result of which, there is a slight decline in eclipsing of the atoms. As I have told you that the planar form is unstable due to high angle strain and the pucker form is more stable form. So this was the story in cyclobutane. Now come to cyclopentane. In the cyclopentane, it has very little angle strain. Almost the angle of pentagon are 108 degree. You see that as the number of ring forming atoms are increasing, the angle are also increasing. In cyclopropane, the angle was of 60 degree, in cyclobutane of 90 degree, and in cyclopentane this is 108 degree. The eclipsing strain is also large here, about 10 kilocalorie per mole if it remained planar. So in planar form, the strain is very high. So planar form is unstable. You see that there exist three different types of uh, conformers in 5-membered rings. One is the planar form, second is a little bent and more bent from two sides. The cyclopentane ring exists as a dynamic equilibrium like that of cyclobutane among various puckered conformations. So here three puckered conformations, two puckered conformations and a planar form are mm, in existing. So uh, the actual structure of the molecule lies in between all these. This is the condition of the cyclopropane, how puckering is um, created in cyclopropane. Now we see the three-dimensional structures of two of the two of the forms. This is the planar form where all the atoms are eclipsing each other, and this one is a puckered form. You rotate in any direction, you will get the same result. You see that at these points, from this and this sigma bond, there is a slight uh, a puckered form is being created, resulting in non-planar form. We have seen that there may be puckering may occur at this site and in two sides. But as the ring flexes, so each of the ring carbon in the puckered conformation for a short time is formed. Although we are showing you here only two of the isomers, and previously in this diagram we have shown three isomeric forms, but you can see that in this rotating molecule many of the isomers can be formed. Actual structure of the molecules lies in between all these. So of these, only these two are more important, which we are discussing in three-dimensional molecules in this case and this one. Now come to the six-membered cyclic compound, which is the cyclohexane. In cyclohexane, there is increased angle strain. In planar form. However, this strain together with the eclipsing strain inherent in a planar structure can be relieved by puckering the ring. So puckering relieves the strain. So puckered forms are more susceptible to form. In the cyclohexane, the possible conformers are shown here in following. The most stable cyclohexane is the chair form. You see that here 6 carbon are present, and most stable form in which the eclipsing is minimized up to highest level is the chair form. The strain, torsional strain, is least in this form, so it is most stable form. The carbon-carbon bonds are close to 109.5 degree, which is the actual in straight chain compounds. You see that there the carbon and carbon ring angle between these is almost 109.5. So it is almost free of angle strain. The angle strain is very least in this case. You can even see the molecule in a larger window. 109.5 degree, 109, 109, all angles are of 109 degree. Now come again to our main screen. Here two types of hydrogens are present, classified due to their position. the axial and the equatorial hydrogens. The axial position point perpendicular to the plane of the ring, whereas the equatorial positions are around the plane of the ring. The adjacent axial positions point in opposite directions, and same is the situation for the equatorial positions. In the given diagram, we will clearly see the difference between axial and equatorial positions. As in this case, only hydrogen at axial position are shown, and here the green color indicates the cyclohexane hydrogen of equatorial positions, and in this case both are shown in the single picture. You see that the hydrogens which are perpendicular to the plane of the ring are axial hydrogens, and this position is the axial position, and the equatorial position is along the plane of the ring. These are the plane of the ring. As the ring is proceeding, the hydrogen present in the same position. More clearly visible in the stick diagram. Red are of axial and blue are of equatorial in this case. Even you can see that how axial positions are in 3D molecules. They are directing at upward direction from the ring, and the equatorial in green color along the ring ring of the system. As the ring goes, the equatorial hydrogen are also present in the same direction. So you clearly have an idea what are the axial and equatorial positions. There is a second type of conformation isomer is also present, which is the boat conformation. You see that in this case the molecule is like a boat, while in case of chair conformation it was like a chair, clearly visible in like an easy chair that you use in your courtyard. And the boat formation, the boat conformation also has no angle strain. However, it does have torsional strain because the conformation is eclipsed at each of the bonds shown in green color. In the boat conformation, although there is no ankle strain, however, there is a torsional strain because the conformation is eclipsed at each of the bond. This is the boat conformation. The flagpole hydrogen are causing steric interaction of the hydrogen atoms inside the bow and the stern, and it destabilizes the boat. These flagpole hydrogens are shown in red color, and this makes the boat conformation less stable. This is, you clearly see that the shape of the molecule is like a boat, so it is the boat conformation as compared to the chair conformation. You see, it is like a chair and boat conformation. There is also a third type of conformer present, which is produced by twisting of the boat to give a twist or skew boat like structure. So it is called a skew boat conformation. This twist relieves some of the torsional strain of the boat and moves the flagpole hydrogen further apart, reducing the steric strain. Consequently, the twist boat is slightly more stable than the boat structure. You see it in this two-dimensional structure and as well as in three-dimensional structure, a skew boat conformation. See that, not like a true boat structure but a skew boat structure. To minimize the strain of the ring. So it is much stable than the boat form, but the most stable form is the chair form. For energy behavior between the different forms, we have this diagram. You can see clearly in this animation that how energy change is occurring between different forms of this series. For example, in the boat case, you see that energy is at intermediate of all levels. In a skew boat, this is the position of the energy and this is the position of 3D structure. A half chair, highest energy, and chair with the lowest energy. And animation shows how variation in different structure is occurring. You can stop it at any point to see the structure of the ring and position of the energy. So now, after discussing these forms, now we see some of the substituted forms, especially in case of cyclohexane, which are the most stable ring system in the series of cyclic compounds. Let's see, when there is only one methyl group is present, what would be the conformation? Remember that substituent on cyclohexane can occupy either axial or equatorial positions. They may be along with the ring or perpendicular to the ring. If they are along the ring, they are called equatorial, and if perpendicular to the ring, they are called axial substituents. And this play an important role in determining their geometry. Remember that generally the equatorial substituents are more stable because of reduced steric interaction. So equatorial position are most stable structures. You see that this is the carbon and this one also the carbon, shown in red the whole methyl group. The hydrogen are also furthest from the other hydrogen of the ring, and carbon is also furthest as compared to the axial position. This is the axial position, which brings a little instability to the molecule. The hydrogen are in close, and even the carbon atmosphere is in such a manner that it is lying close to other carbons, so it is making it a little unstable form as compared to the equatorial form. Methyl cyclohexanes are in equatorial systems. The methyl group is empty to the carbon-carbon bond in the rest of the ring system, as you have seen. See that there are these hydrogens are in close to the hydrogen of the substituent group of the methyl. So this is making them a little unstable. As a result of this, the sample of methyl cyclohexane is composed 95% of the molecules with the methyl group at equatorial position and 5 of the molecules with the methyl group at axial positions. So in the mixture both forms exist, but the amount of equatorial is very high, about 95% of the total molecules. So these two forms may exist in methyl substituted cyclohexane. You see that the ring is of chair conformation in both of the cases, which is the most stable. I have not discussed here in the boat or skew boat conformations, which are less stable, and we are seeing here only the chair conformation, the highest. So there may exist two major conformers of this series. One of the member is in where the methyl group is at axial position, and second where the methyl group is at equatorial position, and of course the equatorial position is most stable form. Now come to the di-substituted, where two methyl groups are present at position number 1 4. Let's suppose we have a molecule with 1 4 positions. At 1 and 4 position there are methyl groups. uh, at 6 membered ring remember that cyclohexane with two or more substitutions can also exist in geometrical isomeric forms, that is cis and trans forms. In the cis form, one methyl is axial and one methyl is equatorial. As you see in this, that one methyl is at axial position and the second methyl is at equatorial position. So this is a cis form. You see in it three-dimensional structure, that in the cis form one is at equatorial position, this one is the equatorial position and second one is the at axial position. The red are the carbon which are in substituted methyl. The chair conformation and the substituents at position number 1 and 4, in which is like this two-dimensional diagram. The second form, which is the trans form, can have again two types. One has both methyl groups equatorial and second has both methyl groups axial. So this one is the where both methyl groups at equatorial position and where both methyl groups are at equatorial position. Enlarge the molecules to a little bit in the window so you can watch them clearly. See that this is the trans form. Both are at equatorial positions, both methyl groups. And in this case, both are at axial positions. Very clearly visible. As you expect that these forms are much more stable as compared to the cis form. You clearly see that environment against each of the atom in this three-dimensional diagram is making less stable than compared to the environment of which atoms in these cases so trans isomers is much more stable than the cis form. And even this form where both methyl groups at equatorial position is most stable and much more stable than this where the methyl groups are at axial position. Now see what would be the conformation of the compound in case when the methyl groups are present at carbon number 1 and 3 positions. So di is substituted at 1,3-dimethyl cyclohexane. Remember that there exist again two types of isomeric forms, the cis and the trans forms. Of these two, cis can have even further into two types. One in which both methyl groups are at equatorial position and one at which both groups are at axial position. This is the axial position, this is the equatorial position. You see that in this case the methyl groups are oriented in such a manner that steric hindrance and strain is least as compared to this structure. Here steric hindrance, the strain is higher as compared to this structure. So a diaxial or axial form is less stable than compared to this form, and this equatorial position is at in a position of being highly stable. There is also another uh, conformer may present in which one of the methyl group is at equatorial position and second methyl is at axial position. This one is the axial position. You see that here in three-dimensional diagram again you see that this axial position is causing the molecule less stable. This is the trans isomeric form of the 1,3 substituted cyclohexane. So trans compound is also less stable than the cis stereoisomer. In this case, cis stereoisomer is much more stable, and of cis forms, this one where the methyl groups are at equatorial positions, it is the highly stable system. And lastly, we see the conformational analysis of the bicyclic compounds. In case of bicyclic compounds, again the trans forms are more stable due to the less steric hindrance. The steric hindrance or steric strain is the main cause of their stability in all the systems. For example, in bicyclo 4,4,0 decane or commonly known as decalene, both rings are fused in two manners. The cis form has the rings joined through one equatorial bond and one axial bond, while in the trans form the rings are joined through two equatorial bonds. This is the cis form and this is the trans form. We have the three-dimensional structures of both. You see that in the trans form the different atoms are uh, situated farthest to each other, making them more stable as compared to the cis form. In cis form, this is steric hindrance and strain, making the molecule less stable. So in this case, this one is the most stable form, which is the trans form. So this was all about the conformational isomerism in ring systems. Hope you have a good understanding as I have used the models, three-dimensional, the very clear pictures to make you the concept very clear. We will meet again in our next lecture of stereochemistry soon. Thank you.